Okay, good afternoon. Let us start our lecture. So last week we discussed about sampling distributions. So basically you have populations and we are interested in some of the characteristics of the population. For example, we are interested in the population mean. So we take a sample, calculate the sample mean, take another sample, calculate the sample mean. So we can have many sample means. So the behavior of this set of sample means can be described by the sampling distributions of the statistics X bar. All right. So so we know that if the random sample represented by x1, xn, each of which follow a normal distribution with mean and sigma square as the variance, then, so if this is true, then the sample mean will follow normal distribution with mean mu and variance sigma square over n, which means that the expectation of the sample mean, we expect the sample mean have the same expectation as the population. So that's very useful. And second thing, the variance of x bar is equal to sigma square over n, which means that it depends on two things. It depends on the variance of x, that means the variation of the population, as well as depend on the sample size. And if the sample size getting bigger, which we can have control over the sample size, then the variance of x bar is getting smaller. All right? But what happens if we don't have these conditions? That means we don't know whether the given populations x1, x2 up to xn follow normal distribution or not. Then how the x bar, the sample mean, behaves. Or in other words, what is the sampling distribution of x bar? So thanks to this central limit theorem, all right, so it says that if your sample size is big, all right, and you have a random sample, you don't need to know the distribution. What you need is the expectation of xi is equal to mu and the variance of xi equal to sigma square. All right. So in other words, all the xi are taken from a population with mean equal to mu and variance equal to sigma square. Of course, there are other forms of central limit theorem which handles different conditions. Like, for example, the sigma square can be different. All right? And so with all this, then we say that x bar is approximately normal. Approximately normal. APP is maybe confusing. It's not it's approximate normal with mean mu and variance sigma square over n. So the result seems more or less the same, but the conditions are different. If your sample are taken from a population, then the x bar will follow a normal distribution. But if the data or the sample is not taken from a normal population, then we can only say that it's approximate normally distributed. All right. How good the approximation, that is a difficult question. So as a rule of thumb, usually when the sample size is bigger than 30, then we presume that the underlying distribution, the approximation should be very good, quite good. All right. In fact, the approximation depends on the underlying distribution. If the underlying distribution is close to normal, symmetric like a bell shape, then the approximation should be very good, even for small sample size, like maybe 20 or 25, or even sometimes go down to 15. All right. But if the distribution is very different from a normal distribution, then you may need a bigger sample size in order to achieve normal distribution. So the power of central limit theorem is that we can get the approximate distribution for the sample mean. For the sample mean. So long as this sample is taken from a certain distribution with expectation equal to mu and the finite variance, sigma square. All right. A very extreme example is like this. I have a population, I have a bunch of ones and zeros, all right? So this population does not follow a normal distribution because you only have two values, but many of them, you have zeros or ones, all right? So the population mean, which is the proportion of ones, call it P, the proportion of ones. How many ones are there? All right. So if you take a sample x1 up to xn, all right. So you basically see only 0 and 1s in the samples. Then you calculate the x bar, which is basically the number of ones plus zeros, all right, and divide by the sample size. This is P hat, or the average. How many ones are there divided by the total number of observations in the sample? So it's P hat. Now, by central limit theorem, this is x bar. So therefore, this P hat is approximately follow a normal distribution with mean equal to P. And in fact, we can also prove that the variance is P1 minus P over N. All right? The sample mean is sigma square over N. Sigma square over N. Because the expectation of X is P and the variance of X is P times 1 minus P. For the population, for each individual, it takes the value 0 or 1. It comes from a random variable, takes only two values, 0 and 1, with probability P being 1, and the variance of this random variable is P times 1 minus P. It's a polynomial distribution. Each of the X follow a polynomial distribution with parameter P. So my point is, you can see that the original population is nowhere close to normal distribution, but the sample mean, which is the sample proportion, basically, sample proportion of ones, that follow approximate normal distribution, provided that your sample size is big enough. All right? You may need a few hundred, not 30. 30 may not be good enough. All right? So you may need bigger sample size. All right? So that is the central limit theorem. When you try to apply a theorem or results, remember to check the conditions for this theorem. All right? So if just remember, central limit theorem saying that something follow a normal approximate normal distribution, then I saw many students apply this to the distribution of the sample, which is not true. It's only the distribution of the sample mean that follow approximate normal. You take a sample, take 1 million out of these populations. What you see is still 0 and 1s. You see 1 million of 0 and 1s. All right? But in nowhere that the sample is normally distributed because you only see 0 and 1s. All right? So you don't confuse the two. The central limit theorem applied to the sample mean, not to the sample value. All right? Okay. So this is, okay, we have a theorem. So we're saying that, all right? There are two parts of this theorem, but basically there's two theorems. One is that with the samples taken from normal with mean, mu, and sigma square, then X bar follows a normal distribution. All right? Maybe follow or distributed as a normal distribution, with mean mu and sigma square over n as the variance. All right? And you don't need the sample size to be big. It can be any sample size. So in other words, this results apply to even 2, a sample size of 2. Even sample size of 1. take a sample with size 1, so the mean is itself. Of course, it still follows a normal distribution with mean mu and variance sigma square over 1. All right, another result is that we have this x follow approximately normal, and x bar is assumed to be follow approximately normal distributions. All right, so this one, approximately normal. Okay, I think my central limit theorem is theorem 5.1. All right, so that one we don't assume any distribution. So in other words, now we have 3 or 2. Okay, the first one is the central limit theorem. We don't need to know the underlying distribution. So long as the sample size is large, then x bar follow approximately normal. Okay, another theorem is saying that if the underlying distribution is normal, x bar will follow normal. Then we twist a little bit. So if the underlying distribution is close to normal, then the x bar is considered as close to normal as well. All right? So this is the difference. We don't need a big samples. If you believe that your underlying distribution is very close to normal, then you don't need a big sample size. You can assume that x bar is approximately normal with mean mu and variance sigma square over n. All right, so you can check this website. All right, so let's look at how we can use these theorems. So now we have a firm produce these light bulbs, and the lifetime supposed to be normally distributed with mean 800 and standard deviation 40. So if x is the lifetime, that x is approximately normal. This is the original x. That means this x referring to the lifetime of each individual light bulb, follow normal with mean 800 and variance 40 square. All right. X is the lifetime of the light bulb. Then find the probability that a random sample of 16 will have an average life less than 775. So in other words, we are asked to find the probability of x bar, 16 of them from a sample of 16, all right, less than 775. So what is this probability? Whenever you are asked to find a probability of a statement, like an event involve a random variable, you need to know the distribution. You need to know the distribution of the random variable. In this case, the random variable is x bar, a sample mean taken from a sample of size 16. That means you take a sample of 16 light bulbs and check their lifetime and then take the average. All right? So we asked ourselves, what is the distribution of this? Because we know x follow approximately normal, therefore x, the sample mean, follow again approximately normal with mean same as x, and variance is 40 square over 16. All right. Remember, it's sigma square over n. That's the variance. So if the standard deviation, it will be 40 divided by square root of 16. All right. Once you know the distribution, the rest are quite straightforward. So now we have all this. So we want to calculate the probability of x bar less than 775. So of course, if you have the graphic calculator, you know how to use it, you may use it. But it's better to get used to this idea. We try to standardize this statement. Standardize means that we minus the mean divided by the standard deviation, minus the mean divided by the standard deviation. So you do something here, you also do the same thing here. So that's why the left and the right-hand side of the inequality by minus the mean divided by the standard deviation. So it approximately means that this statement, this probability of x bar less than 75 is approximately equal to the probability of a standard normal random variable less than minus 2.5. All right, so it looks just minus to 2.5, but there's another meaning to it. It means that this x bar less than 775 is simply saying that what is the chance that X bar is 2.5 standard deviation from the mean. For this statement, Z less than minus 2.5 means that it is 2.5 standard deviation. That means sigma, all right, below, because it's minus, below the mean. The mean is 0, and this is 1. All right. The negative sign means it's below. So it means that what's the chance a standard normal is 2.5 standard deviation below the mean. Below the mean. All right. So here we make use of the property that the standard normal is symmetric around 0. So the chance less than minus 2.5 for standard normal is the same as greater than 2.5. Why I want to do that? Because the table that may be provided to you, or some statistics table, they are working on the right-hand tails. All right, the right-hand tails. So in this case, it's 0.00621. So this probability, or this area, is 0.00621. All right? So in other words, the chance is very small that the sample mean is less than 775 for a sample mean from a sample of size 16 if the light bulb's life follow normal with mean 800 and standard deviation 40. All right, here's another example. We have X bar. Okay, it's a sample of size 75, so n equals 75, and the distribution is, okay, the population, all right, is described by the probability density function. So that means we consider the population of infinite size, but how to describe how this population behaves is described by this PDF f of x equal to 1. In fact, this is a uniform distribution. So you can think of it, you are just, all right, just try to select, all right, or the population is the points taken from this 0, 1, a line segment 0, 1. So you take 75 points randomly and calculate the average. Calculate the average. So asked, find the probability of X bar between 0.45 and 0.55. Can we answer these questions? For just one observation taken from this population. Right? So what is this? 0.1? Am I right? How to get it? Uniform 0, 1. This is f of x, the density. So it's 0 here, then jump 1, and then after we reach 1, becomes 0. So between 0.45 and 0.55, this area falls here with this as the probability. So, of course, what's the length here? 0.1. Height 1, so it's 0.1 times 1, so it's 1. Or you do the integration from 0.45 to 0.55, 1 dx. So that will give you the same answer, 0.1. All right? Then what is probability of X bar falls between 0.45 and 0.55? Is it still 1? Is it still 0.1? No, because this and this two, X referring to an individual observation, taken just from the population, one of them. X bar is take a sample of size n. In this case, n is 75. You take a sample of 75, take the average of these 75 values. That is your X bar. Take another sample of size 75, calculate X bar, and so on. All right. So they behave differently. So now the question that we would like to ask, what is the distribution of X bar? Unfortunately, we don't know. We don't know the exact distribution, but stands for the central limit theorem. So X bar, although we don't know the exact distribution, but this is approximately follow a normal distribution with mean equal to the expectation of x. What is expectation of x? Expectation of x is a plus b divided by 2. Variance of x is equal to b minus a square divided by 12. All right, so it is 1/2 is the mean, and the variance is 1/12 divided by n. N is 75. All right? So in other words, you need to know two things, three things. The mean or the expectation of x, the population, what is the expectation of the population? And what is the variance of the population? You need to know these two. And third is the sample size, whether it's big enough or not. So in this case, 75 is considered big. So now we have an approximate distribution for x bar, so we can proceed to calculate this probability. All right, so the answer is 0.86. All right. So compare with this that I just showed you. For one individual observation, the probability that this observation lies between 0.45 and 0.55 is only 10%. But if you take a sample of size 75, quite a big sample, then the chance that the sample mean lies between 0.45 and 0.55 now increase to 0.866. So quite a big number. So it's very likely that your sample mean will be within 0.45 and 0.55. All right? Okay, another examples. This time we take a sample from a population which follow a Poisson distribution with parameter 0.03. All right. So what is the probability that the sum of the sample will be at least 3? All right. Now, this time we are not asking the probability concerning about the sample mean, but instead we are asked about the sum of the sample. That means we are asked about x1 plus x2 up to xn, which is at least 3. We are asking what is this probability. All right? We are asking what is the probability, the sum, which means that x1 plus x2 plus up to xn at least equal to 3. So greater or equal to 3. While each of these x follow a Poisson distribution with a parameter equal to 0.03. All right. So now you ask yourself, what is the expectation of x in this question? So you have to have some knowledge about Poisson distribution. For Poisson with parameter lambda, then the expectation of x is equal to lambda, or in this case 0.03. How about the variance of x? Variance of x also equal to lambda, the same number. So it's 0.03. All right? But we are not asked to find this probability concerning about the sample mean, but the sum. So here you have to see that there's a link or the one-to-one mapping between the sum and the means. So probability of this x1 up to xn greater or equal to 3. So if I divide both sides by n, in this case n is 50, so I divide by 50. Divide by 50. All right, so this now becomes the x bar, the average of the sample of 50 of them. So sum and average are one-to-one mapping. That means the sum divided by the sample size is equal to the x bar, equal to the sample mean. All right, so I don't know the distribution of the sum, but I can convert it to the sample mean, and I don't know the sample mean, the distribution of the sample mean, but I can approximate by the central limit theorem, provided that my sample size is big and n equal 50 is considered as big. So I have a ways to solve the problem. All right, so the sum greater or equal to 3. All right. So here I applied the continuity correction to make the approximation a little bit slightly better. All right. think of it, because S50 is x1 plus up to x50. This x1, x2 up to x50, these are all integers because they represent the number of occurrence in a Poisson distribution. It's an integer. All these x are integer. So the sum is still an integer. So when we say that this, no matter what this distribution it follows, okay, this must an integer, take integer value. So greater or equal to 3, so you can think of it, all right? If the sum greater or equal to 3, so we have to extend, all right? So we have to extend it to greater than 2.5, greater than 2.5, all right? Although it's a minor point, but it at least we try to compensate on the continuity correction because the original problem, x1 up plus x2 up to x50, the sum is a discrete random variable. And we're going to approximate by a continuous distribution. So we want to at least make sure that these two events are the same so that when I convert it to continuous, so I don't lose too much. All right? So it's greater than 2.5. Now, if this statement is greater than 3, instead of greater or equal to 3, then this side, if it's greater than 3, then that means 3 is not included. So now 3 is not included. So if this is 3, so it can only up to 3.5. So this will be greater than 3.5. All right? So you have to aware of such, so that make sure that your continuity correction are done properly. All right? So after that, I divide by 50. Divide this by 50, so it becomes x bar. So I have to divide the right-hand side of the inequality also by 50. All right? Then, at this point, all right, I further minus the mean divided by the sigma square over, square root of sigma square over n. So this is mu. This is sigma square over n, square root. So I standardize it. So now it becomes, I call this Z, and Z follow approximately a standard normal with mean 0 and variance 1. All right? Now, so each step, from here, this is what we are asked to find. All right? S15 means x1 plus x2 up to x50, greater or equal to 3. This is the question. All right? And then I do the continuity correction, make it this. And then now I try to work, instead of the sum, I work as the sample mean. So I convert it to sample mean. A statement concerning about sample mean instead of sample sum. So I just simply divide 50, the sample size on both sides. Then I standardize, all right, quite straightforward. Then after I standardize, now the question is, this one, I call it Z. So what is the distribution of this one? So this is a standard normal, approximately. All right? So greater than 0.82, and the chance is 0.2061. All right? Okay. So here's another example. So this time, it's the same as before. We are asked the total amount of how many in a week. So, okay. So this individual smokes 5 packets with 20 each in 1 week. So what's the amount of nicotine that consumed? So in other words, we are asking, so if each cigarette has certain amount of nicotine, and then we are asked this question, at least equal to 82. Provided that each of the X, the amount of nicotine in a cigarette, follow mu and this one. So it's just like what we did in the previous example, except that you have to know that we're talking about 100 cigarettes because it's 5 packs. Each pack has 20 cigarettes, and this one, the information given to us is a single cigarette, the amount of nicotine in a single cigarette, which follow a normal, or which has a mean 8.8 and standard deviation 0.1. and no normal distribution mentioned about the negative amount, right? But it's okay, because the sample size is big, we have 100 of them, so we can approximate using the central limit theorem. If you are told that this negative amount follow a normal distribution with mean 0.8 and standard deviation 0.1, then the X bar will follow normal distribution. It's not an approximation. All right, so this one is just like before, and then we can work it out. Okay, example 5. So here we have batch of chemical product is being prepared, and the impurity is a random variable with a mean 4 and standard deviation 1.5. So in this case, we are talking about the amount of impurity, that is our random variable. So different batch have a different amount of impurity, and we believe that this impurity have an expectation equal to 4 and a standard deviation equal to 1.5. All right, so now we take 50 batches independently prepared, all right, and find the approximate probability that the X bar falls between 3.5 and 3.8. All right, so this one again is quite straightforward. How come this one no continuity correction? Huh? Because the amount here, we're talking about the amount of impurity. So this one's supposed to be continuous. So continuous, why still bother to look at continuity correction? So you don't need to correct. You only do continuity correction if the X are discrete. All right? Let me ask you. All the X are continuous. Sorry, not continuous, discrete. Is X bar discrete or continuous? Okay, let's put it this way. X bar, because your X are discrete, so X, sum of the X is still an integer. I mean, let me repeat my question. If Xi's are discrete with the values are integers, or the value of the random variable integers, all right, then the sum of this x1 up to xn, the sample value, sum of the sample value, again is integer. So it makes sense to talk about continuity correction. So the X bar, you divide by n. So it is not an integer, but still discrete, all right? But it depends on the n and the continuity correction. You remember when we talk about continuity correction, it's applied to integer, the rule that we use, because we are talking about something between 2 and 3, for example. Now, but the X bar, when you consider the value of X bar, although they're discrete, let's say I take n equal to 100, all right? Then the sum of X may be from, let's say, 20, the next one is 21, all right? What I'm saying is that, let's say I have 20 of them, all right? Then this one lies value between, let's say, 10 and 11, all right, a difference of 1. Then when I divide by 20, all right, then a difference of 1 divided by 20, so the difference is only 0.05, 0.05. So if you want to correct your continuity correction, it is half of 0.05. Am I right? So what I'm trying to tell you is that when you do the continuity correction, you have to understand the mechanism behind it. So usually it's between two integer values. That's why it is 0.5. We add or subtract 0.5 because it's the midpoint between two values. But when you come to the X bar, the original X are discrete integer, let's say integer. So the sum jump from one value to another value by 1, increase by 1 or difference of 1. From one sum to the next sum, which is difference of 1. But once you divide by n, let's say n equal 20, then you have the difference of this sample mean values is only 0.05. Then half of it is 0.025. If your n is 100, then the difference between the sample mean values is only 0.01, and you have divided by 2, so it's only 0.005, very small number. In that case, we don't bother to do any continuity correction, because the impact of whether you do it or not is not that big if your sample size is big. Okay? Okay, so this one, no continuity, so you just proceed and then get the answer, 0.1636. All right? All right, so this is what we did for example 5. So we don't know the underlying distribution. What we know is the mean equal to 4. Take a sample. The sample mean has expectation equal to 4. All right, lies between 3.5 and 3.8. Then we standardize it. So we get a standard normal distribution with mean 0 and standard deviation 1. So between 3.5 of 3.8 is equivalent to saying that it is the value, it is 0.94 standard deviation, okay, between 2.36 standard deviation below the mean and 0.94 standard deviation below the mean. Okay, this means that 2.36 standard deviation below the mean, this is 0.94 standard deviation below the mean. So the chance falling here and the chance falling here are the same. This one is from the data, x bar, concerned about x bar. This one is after we standardize it, z equal to x bar minus mu divided by sigma over root n. So it's equivalent to saying that the chance that it falls between 2.36 standard deviation below the mean and 0.94 standard deviation below the mean. All right, so the answer is 0.1636. All right, so we have discussed a lot on the sampling distribution of x bar. So now we move on to talk about the difference between two sample means. These two sample means, it does not mean that it is two values from a different sample. Here we're referring to two populations. And each population you take one sample. All right. So the scenario is like this. We are talking about one population, population 1, and population 2. So we take a sample here and take a sample here. So we are looking at two sample means. So we have a sample mean here and we have a sample mean here. So we look at how the difference between these two sample means behaves. All right. This does not mean that a population, you take one and take another one, look at the difference between these two. It does not make much statistical sense. What we do is to look at two different samples from two different populations. All right, so now if the sample size are big, by the way, independent samples, which means that I take a sample from this population and whatever I do here are not linked or related to whatever I do for the second sample. All right, so that is called independent samples. All right, if the sample size are big, all right, then each of these populations have their means, mu1, mu2, and variance sigma 1 square, sigma 2 square. Then the sampling distribution of x1 bar and minus x2 bar. All right, this one is approximately normal. So you have to work out what is the mean and what is the standard or what is the variance. And it's not too difficult to work it out. So the expectation of x1 bar minus x2 bar is equal to expectation of x1 bar minus expectation of x2 bar. So x1 bar is the sample mean taken from the first population, so the mean is mu1. Second sample, x2 bar is the sample mean taken from from the second population. So it is equal to mu2. So it's mu1 minus mu2. All right, so this one is mu1 minus mu2. How about variance of x1 bar minus x2 bar? So it's equal to variance of x1 bar plus variance of x2 bar minus 2 times covariance of x1 bar, x2 bar. All right. Variance, by definition, is the expectation of some square, the square of the difference between the random variable and its expectation. So it can, in fact, we discussed it before. So it's equal to the variance of x1 bar plus variance of x2 bar. All right, that minus 2 times covariance of x1 bar, x2 bar. But because these are independent samples, that means x bar and x1 bar and x2 bar are independent. So therefore, the covariance is equal to 0. So variance of variance of x1 bar is the average, the variance of the first population divided by n1, and the variance of x2 bar is the variance of second population divided by n2. All right? So here, these are the results. All right. So we worked this out just now, and so this is the answer. And so okay, so this is the result. x1 bar minus x2 bar minus its expectation. This, remember, is the expectation of x1 bar minus x2 bar. And this part is the square root of the variance of x1 bar minus x2 bar. All right? So it's a standard normal. So it's not too difficult to see that. We try to standardize it by minus the mean and then over the square root of the variance. So if x1 bar and x2 bar are normally or approximately normal distributed, then this quantity is approximately normal. Right? Okay, so let's look at this example. So we have this television picture tubes from manufacturer A. The lifetime is with mean 6.5 years and standard deviation 0.9. And the other one produced by manufacturer B with mean equal to 6.0 and standard deviation 0.8. Now, here, all this question, this information are given to you. So the population mean lifetime is 6.5. But in practice, we may not know. All right. So here is that we will try to work on the assumption that we have all the information about all this, the mean and the population variance, the population mean and the population variance. So these examples are just trying to illustrate how to compute the probability by making use of the information about the distribution. All right. So we're asked, what is the probability that a random sample of 36 from manufacturer A and the mean lifetime, all right, is at least one more than that of the picture tubes from manufacturer B of a sample size 49. So translated, if this is x36, this is the average or the sample mean of 36 a sample of 36 tubes, all right, minus, let's call it y. Y is 49 tubes from manufacturer B. All right. So we are asked, what is the probability that this one is at least 1 year? So we are asked about this. So this is the question. We are looking at the two sample means. One is a sample from the all this picture tube from the manufacturer A, all right, and the average, which will represent by X36 bar. And the other one is a sample size of 39 of the picture tubes from manufacturer B, and then we've worked out the average of these 49 tubes, lifetime tube of these tubes. All right, so we are asked what's the chance that the difference is bigger than 1. And what other information we know? We know that X1 up to X36, they are normal. Oh, we don't have normal, right? No. So we only know that this one with the expectation of X equal to 0.9 and the square root or the variance of X equal to 0.9. Oh, sorry, this is 6.5. And the variance is 0.9 square. While Y1 up to Y49, we know that Y with the expectation equal to 6 and the variance of Y equal to 0.8 square. So these are the information given to us, and we are asked to find the probability of X36 bar minus Y49 bar greater than 1. So in order to find this probability, you must know the distribution of the difference of these two means. So we work out that the XA bar and XB bar, all right, is equal to 0.5, and the standard deviation is equal to, all right, this is sigma 1 square over n1 plus sigma 2 square over n2, which is the variance of XA bar minus XB bar, all right? So we take the square root, it is the standard deviation. So now the desired probability is this one. You minus the mean, which is 0.5, and then divide by the standard deviation. So you work out this is equivalent to probability of Z greater or equal to how many standard deviation, all right, above the mean, which is, turn out the probability is 0.004. All right? Okay. So, so up to this point, we are talking about sampling distributions about mean, one sample mean, or the difference of two sample means. If allow me to sidetrack. So can we work out what is the distribution of this one? Instead of difference, can we work out the sum? It's similar, all right? You can work out the approximate distribution for this quantity, right? Okay, now we move on to talk about other sampling distribution, all right? But before we talk about the sampling distribution itself, we introduce some new distribution, new in the sense that we have not discussed so far, all right? So the first one is something called a chi-square distribution. It's a very popular and commonly used distribution. So for distribution, we say that if Y is a random variable with such complex form, all right, it follows a chi-square distribution. Okay, don't worry about the form, but at least you know that from this description, what is the range of this random variable Y which follow a chi-square distribution? Is it over the real line or just part of the real line? So it tells us that, okay, it's equal to this quantity only when Y is positive. And then it will be 0 otherwise. That means this Y takes value, this random variable Y, if we follow a chi-square distribution, only takes positive real values. All right? So it's a continuous random variable. So, so in this case, in this whole expression, there's this y, this n, and e, and this look ugly. This is called gamma. It's a capital Greek letter, gamma. Gamma. All right. Okay. So all these are obvious. This is the exponential. Only this part that we need to explain. All right. It's called gamma function. And what's a gamma function? Here's the gamma function. Gamma x or gamma t is equal to integrate from 0 to infinity x to power n minus 1, t minus 1, x to power t minus 1, e to power minus x dx. All right. So this is the gamma function. All right. I have to make a star here. In general, it does not equal to n minus 1 factorial. It's only when n, this part is an integer, then it's equal to n minus 1 factorial. You can show it, not too difficult to show. But t can be any numbers, all right? Because the definition does not restrict that t has to be integer. But if t is if t takes integer value, then it's equal to n minus 1 factorial. All right? So now we go back to this. So it's simply saying that this whole thing is a gamma function evaluate n over 2. So if n over 2 is an integer, then this one is just n over 2 factorial. But if n is odd, then it's not. So, but it's not too difficult to evaluate the values. All right? So it depends on y raised to power n over 2 minus 1. This one, just be careful. This what we mean is n to power n over 2 minus 1. All right? That's what it means. All right? So for any distribution, we need this PDF, probability density function, or probability function to describe it. So here, chi-square is a continuous random variable, so we use the PDF to describe it. All right. We know the range, y bigger than 0, then it takes this form. All right. But you also have to know for a given distribution, usually the infinite number of them belong to that family. That means they are similar. The only difference is some parameters or constants. So in this case, this is a constant. Y is the value of the random variable. So the only thing that indicates that they are different is n. N is n is the parameter of this distribution. Right. Just like normal distribution indicate or characterized by two values, mu and sigma square. For chi-square, it's indices by this n. And we have a name for it called degrees of freedom. Okay, that is something related to its application. We call these parameters the degrees of freedom. All right, so usually there's only one number to identify the chi-square distribution. It's called degrees of freedom. And this degrees of freedom, all right, how this degrees of freedom is linked to the expectation and the variance. All right. So in this case, you can check expectation if expectation of y is equal to n and variance of y equal to 2n, and you can check. All right. Okay. So that's the chi-square distribution. So I illustrate some of the graphs, the graphs of some of the PDFs. So with n equal to 5, so you can see that chi-square 5. So the distribution is quite skewed, all right? Skewed to the right. That means it looks like this. So this is chi-square 5. chi-square 10 is still skew. All right, but how about when it comes to chi-square 20? All right, you can see that it's more or less like a symmetric distribution. All right, so that is how it 20. Okay, so the typo here. Obviously, this is 20, so this should be 20. All right, not 25. It's 20. All right, so for distribution, we know the PDF or PF, that tells you everything, but we also would like to identify the parameters. So chi-square, only one number called n, or called degrees of freedom. Then how is it linked to the expectation and the variance? Okay, so there are some other properties. Okay, here. So if a y is chi-square n, the expectation of y is n and the variance of y is 2n. All right. So for large n, all right, chi-square n is approximately normal with mean and variance. All right. So this is not the central limit theorem, but we can prove that or show that chi-square with a large degrees of freedom will approximate by a normal distribution. Now this is a very interesting result. So it's saying that if you have y1, which is chi-square with degrees of freedom n1, y2 is a chi-square with degrees of freedom n2, and they're independent, then the sum of all this will again be a chi-square distribution with a degrees of freedom equal to the sum of degrees of freedom. All right. So this is very interesting results. So it's saying that, all right, the sum of this bunch of chi-square random variable, independent chi-square random variable, again will follow this chi-square distribution. But of course, the parameter changed. So it changed from n1, n2, or it becomes the sum of all these degrees of freedom. All right. So far, what other distribution have these properties? The sum. Let's say if x1, x2 follow certain distribution, then x1 plus x2 follow the same type of distribution. Do we have any? Besides this chi-square? Normal, right? Normal distribution. If x1 follow normal, x2 follow normal, then x1 plus x2 will follow normal. But of course, you have to figure out what is the mean and what is the variance. All right? They're not the same. And what else? Okay. What else? Check. I think Poisson also have these properties. All right. But definitely chi-square and normal they have these properties. All right. Okay, so that's what we just said. Okay, so there's another very interesting properties is to link two distributions. If x is standard normal, then x squared is a chi-square with degrees of freedom 1. So that means if y is normal with mean mu sigma square, then y minus mu over sigma is standard normal, and I square it, this will follow a chi-square with degrees of freedom 1. All right? So that's the second part of the results. The proof of this one, you don't worry about the proof. All right? You're just aware of the properties that a random variable, which is standard normal, if you take the square of this random variable, then these values, this new random variable, will follow a chi-square distribution with 1 degree of freedom. So now if I have a bunch of xi, which are normal with mean mu and sigma square, then I standardize it and square it, xi minus mu. So I standardize it. all right, and square it. So this is chi-square 1. Now if I have a bunch of them and I add them up, I from 1 to n, then this means that it is 1 plus 1, because each is chi-square 1. So I add all the degrees of freedom. How many are there? N of them. So it's equal to chi-square with n degrees of freedom. So Y follow a chi-square distribution with n degrees of freedom. Just for your information, chi-square distribution is also a very important distribution in statistics, because in statistics, a lot of the times that we would like to know how a test statistic or how a random variable behaves. In other words, what is the distribution of a random variable? All right. So especially we talk about sampling distribution. So we want to know how the sample statistics, or how a random variable come from a sampling, come from a sample, all right, how it behaves. So we may not know the behavior when the sample size is small, but we would like to know when the sample size is big. Or in other words, we would like to know the asymptotic distribution of a random variable. So there are two popular distributions. One is normal distribution, as we learned from central limit theorem. So anything that can be expressed as a sample mean has an asymptotic distribution, which is normal. What you have to figure out what is the mean and what is the standard deviation. Another popular asymptotic distribution is that maybe some other problems with some other random variable of the sample, that when the sample size is getting bigger and bigger, it will approach to a certain distribution, and the distribution is a chi-square distribution. An example which we will not cover here is that for a contingency table, I don't know whether you heard about it, the chi-square test for testing whether two factors are independent or not. So we use a chi-square test, which the asymptotic result is chi-square distribution. All right? So, but at this point, we just have to be aware of such thing. All right? So, of course, how to get the values. So in this, okay, the table that I provide or I uploaded to the Luminous or IVLE, it provides you with a chi-square distributions for given degrees of freedom. Do I have a table here? All right. Okay, so I give you the probability greater than a particular value. So when I write, all right, chi-square n alpha, this referring to a constant, which is this point, such that for a chi-square random variable with degrees of freedom n greater than this value with a probability alpha. So that's what we mean by this point. All right? Probability of y follow a chi-square distribution with n degrees of freedom greater than this value with a probability alpha. And what is this value? This value is here, this point. So I use a notation. The notation is chi-square n semicolon alpha. So this is a constant referring to the probability of a chi-square random variable with n degrees of freedom greater than this alpha with probability alpha. All right. So 1 minus alpha, so referring this part is 1 minus alpha. All right. So in other words, greater than this point is 1 minus alpha, so less than it is alpha. So whenever you use whatever statistical table concerning about chi-square distribution, please read the legend, read the description, whether it's given the left-hand side, the left tail, or the right tail. All right. Okay, so here is Do I have a table here? Okay. So here is a table taken from a textbook. Now, it goes like this. Unlike normal table, this one, normal table is one distribution, the standard normal distribution, one distribution. Chi-square distribution, the infinite number of them. For different n, you have different chi-square. So what I have here is a chi-square, all right, this table, up to 100, up to 100. So it's not 100 distribution. In fact, you can see that after 30, it jumped 30, 40. So I don't have 35. I don't have a chi-square with degrees of freedom 35 displayed in this table. All right. Okay, how to read it? So only one particular distribution given in one row. It only gives you a few points. All right. So these are, okay, the highlight here, for example, 4.865. What does that mean? It's referring to a chi-square distribution with 10 degrees of freedom. Okay? The row heading 10 means 10 degrees of freedom, and 0.95, all right? So in this case, it means that it is a value, okay, for which, all right, greater than this 4.865 is 90%. 90%. All right? 90%. Greater than this value. Oh? So that's how we read it. Okay? So if I want 5%, so this is the value, 18.307. That means for a chi-square distribution with 10 degrees of freedom, with the parameter 10, then the chance greater than 18.307 is only 5%, the column heading, all right? So, so in other words, there is, okay, greater than this number is 5%, less than this number is 5%. 10%, right? 0.90. So less than this number is 10% chance. So that's how we read it. So my point is, we are given a few points. So each point, we know that what's the chance greater than it or less than it. All right. In this table, it is greater that we are talking about. You can see that it's this part. All right. We're talking about the greater part. This referring to the probability greater than this value. This is the degrees, the distribution. We are only given a few points. All right? Chance greater than this number is 99.5, greater than this number is 99%, greater than this number 98%, and so on. So that's how we look at it. All right? Okay. So this is how we read. So for example, I want a chi-square 10 with 0.9, which simply means that I'm looking at a chi-square distribution with 10 degrees of freedom, so that, all right, greater than this number is 90%. What is this number? This number, 4.865. All right? So this is 4.865. All right. You can also using Excel. All right. So Excel, the idea is this: is use the word chi to find something to do with chi-square distribution. This is to find the cumulative probability. All right. This is to find the quantile, the inverse. So this means that, okay, given this B, so this will give you the answer alpha. All right? While this statement is to give this part as alpha and get this answer. All right, the inverse. So it's a quantile thing. So alpha is the probability. So this means that we are looking at a chi-square degrees distributed with 10 degrees of freedom. Look for a value such that less than the value, greater than value is 18.307. All right, greater than this value. So I was wrong. So we're looking at this part. Even Excel, if you use this chi-in, it gives you the upper tails. Sometimes you may lose, but just remember these useful properties. The expectation of a chi-square with degrees of freedom n is n. So in other words, for a chi-square distribution with 10 degrees of freedom, the expectation is 10. So you expect 10 to be somewhere in the middle. So like, if you get answer 18.3, what does it mean? It means that it's much bigger than the expectation. So in other words, we're looking at the upper part of the distribution. All right? So that's one way to check. All right. So this gives you the upper probability, the right-hand tail, the upper probability. Oh, I don't have it here. Okay, just to, I think they may have this chi-square dist for the new version of the Excel. So you have just double check. Okay, why we spend time to talk about chi-square distribution? Because we are interested in finding the sampling distribution of this quantity. Now we are not looking at the sampling distribution of S square. What does I mean? What do I mean here? It means that if I take a sample, I calculate the sample variance S square. Take another sample, calculate the variance, the sample variance. So I can have many sample variants. So how does this behave? All right. So instead of looking at S square, we look at a quantity n-1 S square over sigma square. All right? So this is what we have. So this is S square and sample variance. So this n-1 S square over sigma square, all right, is follow this distribution. This follow a chi-square distribution with n-1 degrees of freedom. All right? But there's a condition, provided that all the x1 up to xn are normally distributed with the mean, mu, and variance sigma square. So this sigma square is important because it appears in this quantity. All right? If you don't know sigma square, there's no way that you can compute n-1 S square over sigma square. All right? But in some other situations, we may not have to know, we don't need to know the sigma square. But the property saying that n-1 square over sigma square follow chi-square. Now if you recall the definition of S square, which is 1 over n summation xi minus x bar square. That is the sample variance formula. So n-1 S square basically is saying that it is summation xi minus x bar square over sigma square. That follow a chi-square distribution with n-1 degrees of freedom. All right. So they are just same expression. Either express it as a sample variance S square, so it's n-1 S square, but n-1 S square is just summation of the square of the difference between xi and x bar. All right, so this is a chi-square distribution. So in other words, if the population is normally distributed, then you take the sample, calculate the sample variance, then this n-1 times the sample variance over sigma square, this is supposed to be a chi-square distribution with n minus 1 degrees of freedom. All right? Okay, so T distribution. So we'll briefly discuss about what is T distribution. What is the significance of this T distribution? Because remember we have this thing. This is standard normal, right? If xi are normally distributed with mean, mu, and sigma square. But what happens if we don't know sigma? So naturally, we will estimate it by the sample standard deviation. So now the question is, what is the distribution of this quantity? You know, you learned it, you heard about it. This is T distribution with n minus 1 degrees of freedom. All right. Okay, so that's why we need to at least have some idea what this T distribution looks like. All right. So first of all, this is how we see the relationship between a standard normal distribution and a chi-square distribution. We can show that if you have a standard normal random variable, all right, and if you have a independent u, which is a chi-square random variable with degrees of freedom n, then the function z over square root u over n will follow, okay, we define it as t, then this t will follow a T distribution with n minus 1 degrees of freedom. All right? Okay, so now the matrix comes. So x bar minus mu over sigma over root n, this one is a standard normal. And in the previous slides, I said n minus 1 s square over sigma square is a chi-square distribution with n minus 1 degrees of freedom. All right? So I have two random variables. The hard part is to prove that they are independent, which is, it can be shown, but it's not within our, in this module. But anyway, we just take the ratio x minus mu over sigma over root n. This is z, this is the z. Then the numerator is n minus 1 s square over sigma square over the degrees of freedom. In this case, the degrees of freedom is n minus 1 over n minus 1. Take the square root of it. All right? It's the standard normal over square root of a chi-square distribution divided by its degrees of freedom. So this is the chi-square distribution divided by the degrees of freedom. So n minus 1 divided by n minus 1. So cancel out. Square root sigma square is sigma. This is the numerator divided by sigma. This is the denominator divided by sigma. So the cancel out. So what do we have? We have x bar minus mu over s over root n. All right? And what is the distribution of this one? It's a T distribution. And what's the degrees of freedom of this T distribution? N minus 1 degrees of freedom. So it looks as if we will do some magic. We replace the sigma, the population standard deviation, by the sample standard deviation. Then it's no more a standard normal distribution, but now it becomes a T distribution with n minus 1 degrees of freedom. All right? These results you have to know, because later on in chapter 6 and chapter 7 we'll discuss this again, how to draw statistical inference about x bar, or maybe draw statistical about the mu, and draw statistical inference about mu1 minus mu2. All right. Okay, so in fact, what is the T distribution? Just now we say that it is standard normal divided by a chi-square over its degrees of freedom and take square root. So that is the t distribution. But in fact, the t distribution have a PDF given by this form. Again, there are two gamma functions here and also a pi here. All right. And as you can see, the whole thing depends on two things. Depends on t and depends on n. T is the value of the random variable. So n is the parameters. In fact, it's also called the degrees of freedom. The degrees of freedom. So t distribution is characterized by one number. And that number is our n here in this expression. And n is called degrees of freedom. And what is the range of the t value, or the value of the random variable t? It is over the real line. Take any values from minus infinity to infinity. All right? So here are some properties about the t distribution. It is symmetrical with mean center at 0. All right? And when it's getting bigger and bigger, the degrees of freedom, it's getting closer and closer to a standard normal distribution. Right? And when n goes to infinity, then it looks like a standard normal. So in other words, this ugly, complicated, complex PDF, this whole thing, where n approach to infinity, getting bigger and bigger, this one can be shown equal to 1 over square root 2 pi e to the power minus t squared over 2. All right? If n getting bigger and bigger. All right? But don't worry, we are not asked to prove that, but you have to be aware of that as the result. The t distribution, all right, when the degrees of freedom is very small, it has its own form. But in fact, it's not too far away from standard normal. But as the degrees of freedom of the n getting bigger and bigger, the t distribution look more like a standard normal. All right? So, for statistical, we are given like this. All right? Now, it is similar to what we just discussed. All right? Again, it's the right tail. So each column, each row gives you a particular distribution. So referring to degrees of freedom 10, all right, then this 1.812, the chance bigger than 1.812 is 5%. That's how we read it. So the chance of a chi-square random variable greater than, with degrees of freedom 10, greater than 2.764 is 1%. Okay, then what is the value for which a chi-square 10 degrees of freedom distribution, t, not chi-square, t distribution with 10 degrees of freedom, all right, greater than a particular value. I want to know what the value of, what value is it? Greater than this number is 95% chance. 95% chance. So I try to look at it. There are no 95 here. No 95 here. So what's the value? So the value is minus 1.812. Why? Because it's symmetric above 0. So greater than this one is 5%. So the image here, all right, if you put it here, all right, then the chance greater than this part is 1 minus this part. This part is 5%, so greater than it is 95%. So just remember the symmetric properties about this t distribution, then you can work out greater than 5% or less than 5%. But how about a value for which greater than it is 25%? So no trick. If this is the table given to you, sorry, we don't know. We only know that the chance bigger than, let's say, chi-square 10, bigger than this number is 10%. So bigger than 25% must be somewhere on the left of this number. That means between 0 and 1.372. That's what I can tell her. All right? 0. 0 is here, right? Greater than 0 is 5%, half of the chance. Greater than 1.372 is 10%. So 25% is somewhere between these two numbers, 0 and 1.372. That's what I can say. Maybe you just take the average of the two. All right. So, okay, I know you can use your graphic calculator or your programmable calculator to calculate all this. But I want you to understand the use of the statistics table, the idea behind. So each row represents one t distribution. And we only give you a few points. So if this information is given to you, how you use them. All right? If exactly 5%, then I can get the exact value. But if I ask you, get me a number for a chi-square distribution with 10 degrees of freedom, such that bigger than that number is 75%. No 0.075 listed in the table. So I would just take the average of these two numbers. Take the average of these two numbers. This number and this number. All right. So I got 0.75. Okay? So, so this is how you use it. All right. And this is important. No, okay, for t distribution it's not so important. The expectation is always 0, while the variance is equal to n over n minus 2. Now this is, now look at the formula. So that means that the variance only defined when n is bigger than 2, it has to be 3. All right? So a t distribution with 1 or 2 degrees of freedom does not, the variance does not exist. Okay, it's the same table. So Excel function, so again, you can use T dot ds. This is to find the probability, the cumulative distribution or the cumulative probability. Okay, this is to find the probability, cumulative probability. This one is to find the quantile. All right? Cumulative probability means that you are given the value and then look at this probability. 2t is 2 tails. I think they also have RT, T dot DST RT. This is the right-hand tail. By default, this is the left-hand tails. While inverse is to give this P and find out what is Q. What is this value? This one is to give you the X, find out what is the P. So this is for TDS, T. This is for T inverse. All right. So basically all the Excel functions are like that. We're looking at T distribution, so start with T. Looking at chi-square, start with CHI. So the INV referring to find the quantile, the DIST referring to find the cumulative probability. All right? So you can try it out yourself. Okay, so, oh, there's still, okay, this is what I just discussed. So x bar minus mu over s over root n is a chi-square, so it's a t distribution of n minus 1 degrees of freedom. All right, I think I have to stop here and then we continue the examples as well as start chapter 6 tomorrow. All right, so I stop here.